Hello everyone. Today I will present a key concept called uniform continuity for multivariable functions. It is a fundamental concept when we learn the mathematical analysis, different from continuity, which guarantees the local stability at individual points. Uniform continuity ensures the global stability across the whole domain. In this video, we will mainly focus on two different definitions for uniform continuity, bridging single variable calculus to higher dimensions. So without further ado, let's first see the definition defined by using the epsilon delta statement. It states that let D be a subset of Rn and f be a function defined on D. We say the function f is uniformly continuous provided that for any epsilon greater than 0, there exists a delta greater than 0 such that for any u and v in D with the norm of u minus v is less than delta, then we have the norm of fu minus fv is less than epsilon. Similar to single variable functions, we can also define uniform continuity by using the sequences. So still let D be a subset of Rn and f be a function defined on it. If uk and vk are any two sequences in D such that the limit of uk minus vk as k approaches to infinity is the zero vector, then we have the limit of fuk minus fvk as k approaches to infinity is also the zero vector. Then you might be curious about the definitions. What's the relationship between the two definitions? So here we provide a theorem stating that the two definitions for uniform continuity are actually equivalent. So why the two definitions are equivalent? Let's see the proof. First, assume that the definition 1 holds and uk and vk are any two sequences in the domain D satisfying the limit of uk minus vk as k approaches to infinity is the zero vector. From definition 1, we know that for any epsilon greater than 0, there exists a delta greater than 0 such that if u and v are any 2 points in D and the norm of u minus v is less than delta, then the norm of fu minus iv is less than epsilon. Based on the condition which says the limit of uk minus vk as k approaches to infinity is the zero vector, we obtain that there is a positive integer capital K such that for all k greater than or equal to the capital K, if the norm of uk minus vk is less than delta, then it deduces that the norm of fuk minus fvk is less than epsilon, and this is for all k greater than or equal to the capital K. So by the definition of the limit, this shows that the limit of fuk minus fvk as k approaches to infinity is the zero vector. Thus, we complete the proof from definition 1 to definition 2. Conversely, if you want to prove that definition 2 implies definition 1, we can consider the contrapositive proof. Namely, we assume that the definition 1 does not hold. And this means that there exists an epsilon greater than 0 such that for all delta greater than 0, there exists 2 points u and v in the domain D such that the norm of u minus v is less than delta, while the norm of fu minus fv should be greater than or equal to the epsilon. Therefore, for every positive integer k, there exists two vectors uk and vk in D such that the norm of uk minus vk is less than 1 over k. Here we just choose the delta to be equal to the 1 over k. And still the norm of fuk minus fvk should be greater than or equal to the epsilon. Notice that The UK and VK are any two sequences in D, and the equation 1 implies that the limit of UK minus VK as k approaches to infinity is the zero vector. If the norm of FUK minus FVK is greater than or equal to the epsilon, by the definition of the limit, we can say that the limit of FUK minus FVK as k approaches to infinity should not be equal to the zero vector. So this shows that if the definition 1 does not hold, then the definition 2 does not hold either. Now let's see the ideas behind the whole proof. For the first part of the proof, we should bear in mind that the same delta controls all the pairs UK-VK once the norm of UK minus VK is sufficiently small. This captures the uniformity across the entire domain D. For the second part of the proof, the idea is that the failure of uniform continuity allows us to construct two sequences UK and VK so that the distance between 2 points UK and VK gets arbitrarily close while their images under the function f remain separated, thus violating the definition 2. To some degree, this theorem is very important because it establishes a sequential criterion for uniform continuity that is equivalent to the epsilon delta statement. Moreover, it provides us a tool for proving or disproving uniform continuity. To prove a function f is uniform continuous, one can verify that for all sequences UK and VK in a domain, satisfying the limit of the difference of the limit of their difference is the zero vector, then it follows that the limit of the difference of their images under the function f is also the zero vector. To prove the function f is not uniformly continuous, we only need to find one special pair of sequences UK and VK such that the limit of UK minus VK as k approaches to infinity is the zero vector, but the limit of FUK minus FVK as k approaches to infinity is not the zero vector. Usually, using this method will be easier than that by using the epsilon delta statement. Also, it does have some practical applications. For example, in the topology, uniform continuity helps to define the uniform spaces, and uniform spaces generalize the matrix spaces. In summary, uniform continuity for multivariable functions extends local stability to global control in higher dimension. And this theorem we've talked before, linking the epsilon delta definition and the sequential definition, is a cornerstone for the advanced analysis in mathematics. That's all for this video. Thank you for listening.